So welcome to the first lecture dealing with molecular shapes. To help us deal with molecular shapes, we're going to use what is known as VSPER. VSPER simply stands for valence shell because the valence shell electrons do chemistry, electron pairs because the electrons like to form pairs, and repulsions because the electrons, of course, don't like each other. So VSPER theory simply says that the pairs of valence electrons around a central atom will try to get as far away from each other as possible. In forming a molecule like mercury dichloride, mercury starts with 2 valence electrons. The chlorines each start with 7. So the mercury puts in 1, the chlorine puts in 1, and we get a bond between the two. Then the second chlorine comes up, and the mercury puts in its second electron. And now the point is we have a bond between each of the chlorines and the mercury. But VSPER says those 2 pairs of electrons want to get as far away from each other as they possibly can. So what's the furthest that they can get away from each other? Well, that obviously means they want to go over and form a bond on the other side of the molecule. And so we end up with that structure, which is linear. All 3 of the atoms are lined up in a straight line. So when you have 2 pairs of electrons, they get as far away from each other as they can. That's 180 degrees. So for the simple 2 electron pairs, we get a simple linear shape. If instead of mercury, we start out with boron, boron has 3 valence electrons. It can therefore form 3 bonds to chlorine. So the first one forms a bond, the second one forms a bond, and it wants to get as far away as it can from that first pair, and it would be linear. But now we have a third pair that comes in and has to go someplace to form a bond. And so they're trying to get as far away from each other as possible, and so we end up with this shape, which is flat. You can see they're all in a plane, and those angles are all about 120 degrees. And so now we have a trigonal planar arrangement for the boron trichloride. For 3 pairs of electrons, we get the trigonal planar arrangement. And finally, if we start with something like carbon, carbon has 4 valence electrons, so it can form 4 bonds. So the first chlorine to carbon forms 1 bond, then the next one forms a second bond, and then the third one forms a bond trying to get as far away as the other 2 as it can. And then finally the last one forms a bond, also trying to get as far away from the others as it can. And in so that case, we end up with this shape. That's a tetrahedron in shape. All those bond angles are about 109.5 degrees. And so we get a tetrahedron when we have 4 pairs of electrons bonding. For the 4 pairs of electrons, we get the tetrahedron shape. Which brings us back to the original question. That is, are any of these 3 molecules, all of which have very polar bonds, actually going to be polar molecules? Well, if we look at the mercury dichloride, chlorine is much more electronegative than mercury, and therefore has a polar bond with the chlorine, the negative end, the mercury, the positive end of the dipole. And then we have 2 dipoles, and they're pointing exactly 180 degrees away from each other, which means they're pointing in absolutely opposite directions. And so we have the case. What happens when 2 guys pull on a rope with exactly the same strength in opposite directions? And the answer is nothing. They cancel out. So even though the mercury dichloride has polar bonds, it's not a polar molecule because the 2 dipoles have the effect of canceling each other out. It's a little harder to see in the case for the boron trichloride because there are now 3 dipoles pointing away from each other. But again, this becomes a simple vector sum problem that they in fact do point away from each other, all at 120 degrees, and the effect is again the same as in the mercury dichloride. They simply end up canceling. And so again, even though the boron trichloride has very polar bonds, the 3 dipoles end up canceling each other out, and so the molecule in total is again nonpolar. For the carbon tetrachloride, we're working in 3 dimensions, but again, they're all pointing away from each other. They're all pointing in opposite directions and pulling and canceling. And so again, even though the carbon tetrachloride has very polar bonds in it, they all cancel each other out, and it's a nonpolar molecule. Well, if the dipoles always end up canceling each other out, how do you ever end up with polar molecules? Well, let's consider a molecule of water, made up of an oxygen and 2 hydrogens. Each of the hydrogen puts in 1, the oxygen puts in 1, we get a bond. The other hydrogen puts in 1, the oxygen puts in 1, we get another bond. And so the oxygen has 2 bonding pairs of electrons around it. VSPER says those 2 pairs should get as far away from each other as they can. The furthest apart they could get would be, of course, 180 degrees, in which case the water molecule would be linear. If the water molecule was linear, the 2 dipoles would in fact cancel. They'd point straight at each other and cancel each other out, and water would be a nonpolar molecule. If water was a nonpolar molecule, it'd have a boiling point of approximately minus 150 degrees Celsius. That is, there wouldn't be any liquid water in the solar system inside the orbit of Saturn. As it turns out, there's a lot of liquid water inside the orbit of Saturn. There's conspicuous amounts of it on this planet. So what's actually going on? Well, what's actually going on is simple. Water is not a nonpolar molecule. It is in fact a conspicuously polar molecule. The angle between the 2 hydrogens is not 180 degrees. It's actually about 105 degrees. But VSPER says they should get as far apart as possible. So why are they ending up at 105 rather than 180 degrees? And that concludes our first lecture on VSPER theory of molecular shapes. You need to go on to the second lecture now.